We're going to begin looking at the scientific method. To begin, we'll have to look at what science is. So by definition, science is going to be the study of the natural world. The class that you're taking is called human biology. So next we're going to look at what biology is. Bio means life, whereas the end of this word, ology, means the study of. So by definition, biology is simply the study of life. Again, since this is human biology, we're going to be looking at how we apply the study of the human as an organism. So we're going to study the human life or body. The scientific method is broadly used in order to gain scientific knowledge. What we're going to do is kind of walk through each step of the scientific method and see how they apply to knowledge gain. So, the scientific method, by definition, is the process of science or the way that science knowledge is acquired. The first step in the scientific method is to observe and generalize. In order to do this, we're going to use inductive reasoning. Inductive reasoning is a generalization that is based on an observation. What we're going to do is apply the specific to the general. The example is that all swans are white. So the specific on here is that the swans are white. The general is that every swan out there is going to be a white swan. Of course, if you've ever seen a black swan, you would know that this is not true. However, the generalization in this case is used to make a prediction. We could, in fact, then do an experiment to determine whether or not all swans are actually white. The example that I'm going to start using in this podcast is the one out of your textbook. That way you can follow along in the textbook and understand well what's going on. So observations. The textbook states that rats are given drug X. Those rats have a lower blood pressure than rats that are not fed the drug. Additionally, there may be somebody who is in Canada who is independently doing research. They also show that this drug X lowers blood pressures in dogs and cats. So now we know that drug X not only lowers blood pressure in rats, but it also does it in dogs and cats. Therefore, we can make a generalization. The generalization would be that this drug X, is able to lower blood pressure in all mammals. The next step in the scientific method is to formulate a hypothesis. By definition, a hypothesis is a tentative statement about the natural world that can be tested. The example hypothesis for our situation is that if drug X would be safe and effective treatment for high blood pressure in humans. So again, what we're saying is that this drug was effective on rats, dogs, and cats, and now we want to hypothesize that it is effective on humans and possibly go ahead and test that. Step 3 in the scientific method is to make a testable prediction. This is a working hypothesis. In the past, you may have learned that a hypothesis has to be stated in an if-then statement. If we give the drug to humans, then it will lower blood pressure. So we're going to take and make a working hypothesis. In this case, we're going to use deductive reasoning. Deductive reasoning is applying the general case to the specific. So our prediction is going to be that drug X is a safe and effective treatment for high blood pressure in humans. That's the general. Here's the specific. 10 milligrams a day of drug X will lower blood pressure in people with high blood pressure within 1 month. So we're going to say exactly how much drug they're going to get, for what duration they're going to be taking that drug. Then, of course, what we have to do is experiment or observe. Recognize that sometimes an experiment is reasonable, able to be taken place, such as the example that we're going to do. Other situations say that an observation is what the actual test is going to be. An experiment, by definition, is a planned and executed manipulation of the natural world designed to test your prediction. In science, we're going to use what we call a controlled experiment. This is conducted under specific conditions. we have to account for all variables. So what we want to do if we're doing this particular experiment with drug X is possibly keep these people on a similar diet, a similar exercise program, etc. Because what we want is to know if it's actually the drug that's working or if it's another variable. So we're going to try and account for all variables involved. The controlled variable then is our factor of interest, what we are concerned about. So in this case, we're concerned, of course, with whether or not drug X is an effective mechanism for lowering blood pressure in humans. The experiment example then, if we were to carry out this particular experiment, would be that we would select a large group of humans with high blood pressure. It's really, really important to select a large group of humans. The more people we have in an experiment, the more reliable those results are. Take, for example, if we had 5 people in a room and I asked those 5 people if they liked tomatoes, and all 5 people said, yes, I like tomatoes, then we could assume that everybody likes tomatoes, although we know that that's not true. Therefore, the more people we have in an experiment group, the better. We're also going to randomly divide the group into experimental and control group. We don't say want to have men versus women, nor do we want to have our experiment divided amongst race. What we want is to have a random division of participants in the experiment. Both groups then are going to be treated the same, except the experimental group gets the drug. The control group then is going to get the placebo. A placebo is, of course, they're going to be given a medication just like the experimental group does, but it's going to be a sugar pill or something that doesn't actually contain the drug, so they're not necessarily going to know that they don't get the drug. If the experiment is called blind, that means that the subjects who are getting the drug don't know who's getting treatment. In other words, you wouldn't know if the pill you were taking was an active drug or if it was a placebo. If the experiment is double-blind, that means that the subjects who are taking the drug and the people who are administering the drugs don't know who's getting the treatment. Only the people who have designed the experiment will know. This eliminates any bias. We don't want people to have the mind over matter situation where they know they're getting the drug and so they do much better with the treatment. At the end of the month, we're going to measure the blood pressure of the individuals in the experiment. If the experimental group's blood pressure is lower, then the prediction is verified and the hypothesis is supported. However, that's not always going to be the situation. This picture here just shows you visually how we're going to arrange our experiment. We're going to select a large number of subjects for our experiment. We're going to randomly divide them into 2 groups. One group is going to be the experimental group and they're going to get the treatment. The other group is going to be the control group and they're going to receive the placebo. After our 1-month period, we're going to observe and or take measurements, in this case blood pressure, and then we're simply going to compare the results. If the blood pressure of the experimental group is lower, then yes, the hypothesis is supported. If the blood pressure is not lower of the experimental group, then we're going to modify the hypothesis to fit new findings. Step 5 then is just that, to modify the hypothesis as necessary and repeat steps 3 and 4. Just because our results of the experiment do not support the hypothesis does not mean that we've wasted any time or money. Half of science is in fact getting results that don't support the hypothesis, and that way we're able to narrow our criterion for an experiment. So, if the prediction is proven false, then of course we're going to modify the hypothesis. We're going to use this to verify results and then to test more specifically. Let's say that drug X does lower our blood pressure. We still need to know how this blood pressure affects maybe women, maybe pregnant women. Pop some of these up here. So pregnant women, what effects does it have on the kidney? Maybe what effects does it have on the liver? So different side effects and such. We need to get lots and lots of information on this particular drug. So even if we did support the hypothesis, we're still going to go back and do further testing. This is just a pictorial representation of the scientific method, showing you that in the event that we have a hypothesis that doesn't necessarily, or results that don't support our hypothesis, we have to go and repeat steps 3 and 4. So we have to make a new testable prediction, and we have to complete a new experiment or observation. After the scientific method, so after we've collected all of our data and done all of our experimentation, we should make the findings known. We're going to do that by publishing in a peer-reviewed journal. This is so other people out there doing similar research can learn from our experience. Additionally, it's to save time and money. People don't necessarily need to do the exact same experiment over and over in the event that it's already been done. They can, of course, take the data, modify it, and create their own experiments, and then just to get the knowledge out to the scientific community. A well-tested hypothesis becomes a theory. A theory, by definition, is a broad hypothesis that has been extensively and tested and supported over time with a high reliability. That means that every time this experiment is completed, we're getting the same results. So much so that it has become, of course, a theory. Atomic theory, the theory of the atom and the structure of an atom, is a good example of a theory. Nobody really questions that an atom has a nucleus, and inside of that nucleus are some subatomic particles, and then surrounding that nucleus there are also subatomic particles. So over time, that theory has held up.